2024 A-Level Combined Mathematics Paper 2 Part A question number 5. This question has to do with circular motion and centripetal acceleration. The question says a particle P of mass 2m is connected to two fixed points A and B lying on a vertical line by two light inextensible strings each of length L. So as you can see, our particle P is connected to 2 points A and B by two strings each of length L. The particle P moves in a horizontal circle with a constant angular velocity of omega, with both strings taut and both making an angle of theta in between c and pi by 2 radians to the vertical as shown in the figure. So in the figure we can see our particle P is not standing still. Instead, it is moving in a circle like this, and as it moves, both of the strings are kept taut, meaning that there's a tension in the strings, and both of the strings make an angle theta in between their directions and the vertical that is also equal to the line in between the points A and B. Now given this information, we are asked to show that the tension in the string AP, which is the top string here, is equal to m times bracket L omega squared plus g times secant of theta. Now to start off with this question, let's first mark everything that is not already marked in this diagram in the same diagram itself. So first, we are given that particle P has a mass of 2m. However, in the diagram, we have not marked the force due to gravity occurring from this mass. So let's first mark that the particle P has mass of 2m, and therefore it would have a downward force on it of 2m times g, or 2mg. Now in addition to this, we are asked to find the tension in the string AP. However, both strings are under tension, and therefore I need to mark tension in the string AP and another tension in the string BP. So therefore, since I want to find the tension AP, I'll mark that tension as T1 like so, and I'll mark the other tension in the lower string as T2. Now, in addition to this, there's one more thing we need to mark. Since our particle P is rotating in a circle like this, there will have to be some kind of centripetal acceleration of the particle P towards the center of our circle in order to balance out the tangential velocity and make sure that our particle P maintains the same tangential velocity and it keeps changing its direction to go in a circle. So due to that, I can mark an acceleration of the particle P towards the center of this circle like this, and I'm going to mark it like this and call it F. Now we can of course find the value of F, and we'll be doing that shortly, but for now I'm going to mark the centripetal acceleration as F. Now with this, we are ready to apply F equals ma in two perpendicular directions in order to find the values of T1 and T2. In our case, of course, we don't want T2, we only want T1. So in this case, I'm going to say applying F equals ma, and I'm going to try applying F equals ma in two perpendicular directions. In my case, since I have this direction acceleration and perpendicular to that a downward direction of 2mg force, I can take the vertical and horizontal directions to apply F equals ma. So in my case, I'm going to apply upward and inward. You can of course write downward and leftward or something like that, or rightward, but you just need two perpendicular directions in this situation in order to find the values of T1 and T2. So in my case, I'm going to apply F equals ma vertically upward, and I'm also going to apply F equals ma in the direction towards the center of the rotation of the particle P. Now, considering the upward direction, I can see I have a vertical component of T1 since we don't have the full T1 because of the angle. I also have a downward vertical component of T2, again not the full T2 because of the angle, but I also have a full 2mg in the downward direction. Now due to this, if I consider the components, I'm going to have T1 times some trigonometric component, and then I'm going to have minus T2 since it's in the downward direction times some trigonometric component, and minus 2mg. Now, considering the trigonometry here, we can see in this triangle, if we consider the hypotenuse to be T1, we can see the vertical component here is going to be T1 cosine of theta, since this side is the adjacent side to the angle theta. So due to that, the trigonometric component that we have here is cosine of theta. So here, the vertical component of T1 is T1 cosine theta. Now similarly, if we consider this triangle and this angle theta, we can see the vertical component here, considering T2 as the hypotenuse, is going to be again T2 cosine of theta, since the side length that we want is the adjacent to the angle theta. So due to that, we can write this as being negative T2 times cosine of theta. Now that's the order of the forces. On the right hand side we have MA. On the right hand side if we write MA, we have M, which is 2M, times A, which in this case, since our particle is in equilibrium, so it is not moving vertically, it's only moving horizontally, it is equal to 0. Therefore, if we simplify, we are going to get only 0 on the right hand side. So we get T1 cosine of theta minus T2 cosine of theta minus 2mg equals 0. And that's going to be equation number 1. Now similarly, we can apply efficacy M in the horizontal direction, and I'm going to apply it radially towards the center of the rotation of the particle P. Now considering that the force that we have here are the horizontal component of T1, the horizontal component of T2, and nothing else. And as for the acceleration here, with the mass of 2m and the acceleration of f in the inward direction. So according to that, I can say that on the left hand side the forces are T1's horizontal component, which if you look at the triangle here, since this side that we want here is opposite to angle theta, it is going to be T1 sine of theta, and therefore we can write T1 times sine of theta plus, and considering the other forces, for T2 here also, if you consider the horizontal component, it is opposite to the angle of theta, where this is the hypotenuse, and therefore it is T2 sine of theta. So therefore we get T1 sine of theta plus T2 sine theta and no other forces. On the right hand side, we get mass times acceleration, which is 2m times f, and that is equation number 2. Now other than these two, there is one more equation we can get, and that is the equation for f. Now as we know, whenever you have any kind of centripetal acceleration where you have either the tangential velocity known as v or the angular velocity known as omega and the radius known as r, you can either write the centripetal acceleration in this direction, let's say a, as a equal v squared divided by r, or a equal omega squared times r. Both of these are equal, since of course omega is equal to v over r. Now in our case, we have omega but we don't have v, but we of course don't need v since we have omega. But what we don't have is the radius of a circle, at least we don't have it directly, but we can easily find it by considering the trigonometry here. So in this situation, we can see this length AP is of length L. Similarly, of course, the length BP is also of length L. Now if we consider this right angle triangle here, the hypotenuse of the triangle is L, and if we consider the radius here, the radius is the side length opposite to the angle theta up here. Due to that, we can see this length L times sine of theta is equal to this side length, which is also equal to the radius of the circle that the particle P is rotating on. So therefore, the radius here is L sine theta. Now according to that, we can say from centripetal acceleration, our f, our centripetal acceleration, according to the formula a equals omega squared times r, must be equal to omega squared times the radius, which is L sine theta. That's going to be equation number 3, and with that we can substitute 1, 2 and 3 into each other in order to find the value of T1. Now to start off, we can take equation number 1 and we can see if we take 2mg to the other side, we get T1 cosine theta minus T2 cosine theta equal 2mg. And we can also see if we divide both sides by cosine theta, we get from equation number 1 T1 plus T1 minus T2 rather, equals, and on the other side we have 2mg divided by cosine of theta. And in the question we can see, in our final answer we have secant of theta, and 1 divided by cosine of theta is in fact secant of theta. So instead of writing this as 2mg divided by cosine theta, I'll write it as 2mg times secant of theta. Now similarly, if we consider equation number 2, we can see dividing both sides by sine theta, we can get this thing to the other side and write that T1 plus T2. If we take equation number 2, we get T1 plus T2 equals, on the other side we have 2mf divided by sine of theta. Now we can do another substitution here. We can see from equation number 3, instead of t, we can substitute omega squared L sine of theta. According to that, we can take this equation and use 3 on it, and from that we get t1 plus t2 being equal to 2m times f, which is omega squared L sine theta divided by sine theta. So omega squared L sine theta divided by sine theta, which if we cancel these two out, we get left 2m times omega squared times L. So we get 2m omega squared L. I'm going to call this equation number 5, or rather equation number 4, and this equation at the bottom here, equation number 5. Now with this, we can finally find the value of t1. So from this, you can see, if you add equation number 4 and equation number 5, we do 4 plus 5, we can see the minus t2 and plus t2 will cancel each other out, and on left hand side we will have t1 plus t1, which is 2t1, and t1 is of course the tension that we want. On the other side of our equation, we can see we have 2mg sec theta plus 2m omega squared L. So therefore we get 2m omega squared L plus 2mg secant of theta. And our final answer, we can see we're supposed to get the tension in the string AP as in the tension T1 equal m times L omega squared plus g secant of theta. And we can see if we divide everything by 2 and then we factor out the m in this equation and this expression and this expression, we can see we get left with omega squared L and g secant of theta. So therefore we have our answer. All we have to do is do the simplification, and we can see from that we get T1 equals m times, and then here we get omega squared L, and then plus g secant of theta. So plus g secant of theta, and that is the final answer to this question. So now finally, let's go up and discuss the marks awarded for this question. So at the start of the question, when you mark all of this stuff in the diagram, you actually don't get any marks. Instead, you get marks when you apply Figures MA using the stuff you marked in the diagram to get equations like this. Specifically, when you get the vertical equation like this, exactly like this, of course, you get 5 marks. And similarly, when you get the horizontal equation, of course, exactly like this, you get another 5 marks. Now after that, when you find the value of centripetal acceleration like so, and find that F is equal to omega squared times L sine of theta, you get another 5 marks. And from that, when you substitute into this second equation and simplify to get T1 plus T2 equal 2 times m times omega squared times L, you get another 5 marks. And finally, when you combine the equations of T1 minus T2 and T1 plus T2 to get 2T1, and then simplify to get T1 and get the final answer, T1 equals m times omega squared L, or rather omega squared L, not omega squared L squared, I made a small mistake there, omega squared L plus g secant of theta. When you get that last equation there, you get a final 5 marks. And with that, we are done with the discussion of this question. So I hope you enjoyed. If you have any feedback or questions, post them in the comments down below. Thank you for watching, and goodbye.